Welcome students. Now that you have understood the meaning of limits, now we'll shift our attention to the next topic, which is called the continuity of a function. Continuity of functions. So this term continuity is a very intuitive term. So whenever you say that something is continuous, it simply means that it does not break. So if I say that some object is continuous, that means it does not have any breakages. You have a continuous increase in price, that means you don't have any specific jumps in the price. The price of an object is increasing continuously. That means it does not increase in specific jumps. It increases continuously without any breakages. So continuity in mathematics, if I say that a function is continuous, if I say that a function is continuous at a point, it simply means that the graph of the function does not have any breakages at the point that we are talking about. And if I say that the function is discontinuous at a point, that simply means that the graph of the function is somehow breaking at that point. So this is the geometric significance of the topic of continuity. So here in this topic we check the continuity of the functions in terms of their graphs. So for example, if you take the graph of f of x is equal to sin x, take the graph of f of x is equal to sin x. So how does the graph look like? You know the graph of sin x. So the graph of sin x is a wave-like curve like this. So as you can see, this curve is continuous. There is no breakage at any point whatsoever. There is no breakage. The curve is not breaking. The curve is moving continuously. So we say that the function sin x is continuous at every value of x. At every value of x. Every value of x. So next, if you take the function f of x is equal to the integer part of x. F of x is equal to integer part of x. You know the graph of this function also. You have a stair-like function, right? You have a stair-like function, stair-like graph. So the graph looks like this. Graph looks like this, right? So you have closed, open, closed, open, closed, open, closed, open, so on. So as you can very clearly see, this graph has a breakage at integer values. This graph breaks here and starts here, breaks here and starts here, breaks here and starts here. So we say that the function integer part of x is discontinuous. At which points? It's not breaking at every point. So the graph of integer part of x is breaking at integer values of x. So I say that integer part of x is discontinuous at values of x which belongs to integers. And it is continuous at the remaining points. As you can see, in between the integers, the graph is not breaking. So integer part of x is continuous at all values of x which are not integers, and it is discontinuous at the values of x which are integers. In the same way, as we have seen in our 11th class, we have different functions having different graphs. So when you observe the graph, you can see whether they are continuous or discontinuous. If they are breaking, they are discontinuous. If they are not breaking, they are continuous. So this is the physical meaning of the continuity of a function at a point. Now, let us try to understand the analytical meaning of continuity or the mathematical meaning of continuity. So now the question is, what is the mathematical or analytical meaning of continuity of a function at a given point? So let us say that you have a function y is equal to f of x. So as you can see, physically, you can see that this function is continuous. There are no breakages in this graph. Now, what is the mathematical meaning of this? So you can very clearly see visually that there are no breakages whatsoever on this graph. So now, what does this translate into in terms of mathematical expressions or mathematical equations? So now, let us try to analyze the continuity of this graph at a point A. So let us take a point corresponding to x is equal to A. So corresponding to x is equal to A, this is the point on the graph. So as you can see, f of A, let us call this equal to L. That is the value of the function, the functional value of this graph at x is equal to A is L. Now, if a function has to be continuous at this point, so what should happen is the limit of this function as x tends to A. So limit x tends to A plus f of x should also be equal to L. That is, as x tends to A from the right hand side, this function has to approach this value L, and limit x tends to A minus f of x should also tend to the functional value at x is equal to A. So if all the three happens, then we say that the function is continuous at x is equal to A. So what is the mathematical equation which ensures continuity? At x is equal to A, limit x tends to A plus f of x has to be equal to limit x tends to A minus f of x has to be equal to f of A. The right hand limit has to be equal to the left hand limit. That means the limit has to exist. So both these conditions ensure that the limit exists. So the limit has to exist and the limit has to be exactly equal to the functional value. So if the limit of the function is equal to the functional value, then we say that the function is continuous at that specific point. So this is the most important condition for this chapter. So most of the questions, 90% of the questions on this chapter depends on this formula. So this formula has to be remembered very nicely. So limit x tends to A plus f of x is equal to limit x tends to A minus f of x is equal to f of A. So I want you to write this a lot of times so that you get familiar with this formula. So this is the condition for continuity of a function at a given point. Now, what are the different cases where the function may not be continuous? So as you can see, if the graph of this function is, if a graph of some function is like this. So this is a point where f of x is not defined. Hollow dot means that f of x is not defined at this point. At this single point, at this point, the function is not defined. So obviously if the function is not defined, you have a small breakage there. Corresponding to this point, there is no image, there is no value of y. So the graph comes until this point, it has a small breakage and then it continues. So this is one example of discontinuity. So if f of A is not defined, so if a function is not defined at any specific point, it will be a point of discontinuity. Next, there is one more case. If the function is defined, but it is not same as the limiting value. At this point, both the right limit and left limit are reaching this point, but the functional value is somewhere else. So if limit exists, but limit is not equal to the functional value, then also the function is not continuous. That is, limit x tends to a, f of x is not equal to f of a. In this case, you get a graph like this. As you can very clearly see, there is a discontinuity here. So if the limit is not equal to the functional value, then also the function is discontinuous. And the third case is if the limit does not exist. It is the right limit is different, the left limit is different. So if you have something like this, graph like this, the right limit is tending to this value, the left limit is tending to this value. So the right limit is not equal to the left limit, hence the function is discontinuous. You can very clearly see the discontinuity. So if limit x tends to a plus f of x is not equal to limit x tends to a minus f of x, then also the function is discontinuous. So these are the major reasons for a function to be discontinuous. One is if the function is not defined at that point. The second is function is defined but it's not equal to the limit. And third is if the limits are not defined. That is, if the right limit is not same as the left limit. If the limits are not defined finitely. That is, if the right limit is not equal to left limit, then we also say that the function is discontinuous. Right? So if the function has to be discontinuous, if the function has to be continuous, limit x tends to a plus f of x should be equal to limit x tends to a minus f of x should be equal to the functional value. This is the most important condition of this chapter. For example, if you take this function f of x is equal to x square minus 4 by x minus 2 if x is not equal to 2 and 2 if x is equal to 2. It is a piecewise defined function. So as long as x is not equal to 2, the definition is this. If x is equal to 2, the definition is this. If you are asked to check the continuity of this function at x is equal to 2. So what you just need to do is limit x tends to 2 f of x. So again, the right limit and left limit, you have to decide whether you need both the limits or you can do with direct limit. We have seen in the limits that we can directly find the limit if the function is good. If the function is not differently defined in the different neighborhoods, you can directly find the limit. So limit x tends to 2 f of x is nothing but limit x tends to 2. X tends to 2 means x is not equal to 2. So this function works x square minus 4 by x minus 2. So that is limit x tends to 2. X square minus 4 is x minus 2 times x plus 2 by x minus 2. So the indeterminacy gets cancelled. So once the indeterminacy is cancelled, you just substitute the value. So you get 4 as the answer. That means the value of limit x tends to 2 f of x, both the right limit and left limit are tending to 4. But what is the functional value at x is equal to 2? Is equal to 2. So here, as you can very clearly see, the limit is not equal to the functional value. So if the limit is not equal to the functional value, then the function is not continuous. So if you draw the graph of this, the graph will look something like this. So this function is x plus 2 if x is not equal to 2. The graph looks like this. So at x is equal to 2, the limit is going to 4, but the functional value is 2. The graph looks something like this. So the limit is not same as functional value, hence the function is discontinuous. So if you take another example, like f of x is equal to integer part of x. So as you can see, the graph of the function looks like this. So if you take any integer value, that is, if you take the value 1, so the right limit at x is x tends to 1. Limit x tends to 1 plus integer part of x is equal to 1. As x comes from the positive neighborhood of 1, the limit is equal to 1. Limit x tends to 1 minus f of x, integer part of x, is equal to 0, as x tends to 1 minus integer part of x goes to 0. Here the right limit is not same as left limit. Here the right limit is not same as left limit. Hence you have a jump or a discontinuity. Hence again we say that integer part of x is discontinuous at x is equal to 1. We have other points of discontinuity also for this function. And for example, if you take f of x is equal to 1 by x. So what about this function at x is equal to 0? So as you can very clearly see, f of 0 is not defined, because f of 0 is 1 by 0, which is not defined. Hence, if a function is not defined at any specific value of x, at that point the function is discontinuous. Discontinuous at x is equal to 0. That means if the function is not defined, it is discontinuous. If the function is defined but the limit is not defined, then also it is discontinuous. If the function is defined and the limit is defined but these two are different, then also the function is discontinuous. So this is the mathematical meaning of the discontinuity of a function at a given point. So now let us look at the terms right continuity and left continuity. Right continuity and left continuity. So if limit x tends to a plus f of x is equal to f of a, that is the limit from the right hand side, if it is equal to the functional value, we say that the function is right continuous. Function is right continuous. And if limit x tends to a minus f of x is equal to f of a, that is the limit, the left hand limit is equal to the functional value, we say that the function is left continuous. And if the function is both right continuous and left continuous, that means the function is continuous, right? If the function is both right continuous and left continuous, then we say that the function is just continuous at x is equal to a. So in terms of graph, it looks something like this. In terms of graph, so if you take xy plane, so if you have a function like this, as you can see, this function is discontinuous at x is equal to a. This function is discontinuous at x is equal to a. But if you want to talk about specific right continuity and left continuity, so this function is right continuous because the right hand limit is same as the functional value. This is the functional value, and the right hand limit is also same. The left hand limit is something else. So this function is not left continuous but right continuous. And similarly, if you have a graph which looks like this, this function is left continuous. That is, the left hand limit is same as the functional value. The right hand limit is something different, right? So if a function is both right continuous and left continuous, then we say that the function is continuous at the point A. So now let us look at the meaning of continuity of a function in an interval. So till now we have seen the meaning of continuity of a function at a point. So if you have a function whose graph is something like this, if you are talking about the continuity in an interval a comma b, if you are talking about the continuity in an interval a comma b, so a function f of x is said to be continuous in open interval a comma b. In the open interval a comma b, if it is continuous at every point in this interval. If it is continuous, at every point every point in the open interval a comma b. That is, at every point between a and b, the function has to be continuous. Then we say that the function is continuous in open interval a comma b. Next, if a function is continuous in closed a comma b, so what is the minimum criteria which has to happen if a function is continuous in closed AB? So there are three conditions. If a function has to be continuous in closed AB, it has to be continuous in open AB. That is, between all the points in A and B, it has to be continuous. And it has to be right continuous at A. It has to be right continuous at the starting point, and it has to be left continuous at the ending point. So if these three conditions are valid, we say that the function is continuous in closed a comma b. That is, if a function has to be continuous in closed a to closed b, then the function need not be completely continuous in the point A. So it has to be at least right continuous. That is, left side the graph can be like this. It has to be right continuous at x is equal to a. That's a minimum condition. If it is completely continuous, it's very good. But the minimum required condition is that the graph has to be at least right continuous at x is equal to a, and it has to be at least left continuous at x is equal to b. That is, the left limit has to be equal to the functional value. So the graph can be like this also. So I say that if the graph is like this, the function is continuous in closed AB. That is, in between A and B, it has to be continuous. There are no breakages. At x is equal to A, it has to be at least right continuous. And at x is equal to B, it has to be at least left continuous. If it is completely continuous, well and good. This is also continuous in closed AB. This is also continuous in closed AB. So at x is equal to a, it need not be completely continuous. So if it is right continuous, then it is okay. At the end point, if it is left continuous, it is okay. But if at x is equal to a, it is not right continuous, then closed AB will not be continuous. So I hope you understand the conditions. So if a function has to be continuous in closed AB, the three things that you need to check is between open A and open B, it has to be continuous at all points. At x is equal to a, it has to be at least right continuous. At the end point, it has to be at least left continuous. So these are the three conditions which needs to be valid so that the function is continuous in closed A comma B. So once you understand the meaning of continuity, one of the very basic question is you'll be given a function and you'll be asked to discuss the continuity of this function at certain points. For example, f of x is defined as x if x belongs to integers, 0 if x does not belong to integers. You are asked to discuss the continuity of f of x at integer values of x. So at each integer value, you're asked to check whether the function is continuous or discontinuous. Discuss the continuity means that you are asked to check whether it is continuous or not. So you're asked to discuss the continuity at integer values of x. So let n be an integer. Let n be an integer. So let us try to see the continuity or discontinuity at this point at x is equal to n. So what is the formula for continuity? So limit x tends to n plus f of x, limit x tends to n minus f of x, and f of x. If these three are equal, then the function is continuous. If these three are not equal, then the function is discontinuous. Now let us try to find each of this. So this is equal to. So if x tends to n plus, that is integer plus, that is the neighborhood of an integer number. Obviously the neighborhood of an integer number consists of all non-integers, right? So if you take 2, 2 plus contains all the real numbers around 2. So they are not integers. So as x tends to n plus, my f of x will be 0 because x is a non-integer. So limit x tends to n plus 0, which will be equal to 0. Similarly, at x tends to n minus, n is an integer, so n minus is a non-integer. The neighborhood of an integer consists of non-integers. So limit x tends to n minus, so this is also equal to 0. So this is equal to 0. So the right limit as well as left limit is equal to 0. Now what is the functional value? The functional value of x is equal to x if x belongs to integers. So n is an integer, so f of n is equal to n. So if 0 equal to 0 is equal to n, then it is continuous. That is, the function f of x is continuous at n is equal to 0. At 0, the function is continuous. At all other integer values, if n is not equal to 0, that is, integers other than 0, f of x is discontinuous. So my function is continuous at only 0, which is an integer value. At all other integer values, my f of x is discontinuous. So that's the analysis of this function at different integer values of x. So in this question, you're asked to examine the continuity of f of x is equal to mod sin x by x if x not equal to 0, 1 if x is equal to 0, at x is equal to 0. You're asked to examine the continuity of this function at x is equal to 0. So how do you check the continuity? You have a formula. So you need to check whether the condition for continuity holds good or not. So limit x tends to 0 plus f of x, limit x tends to 0 minus f of x, and f of 0. So these are the three quantities which you need to find. If these three turn out to be equal, then the function is continuous at x is equal to 0, otherwise not. So let us try to find each of this. So limit x tends to 0 plus, in the positive neighborhood of 0, as long as x is not equal to 0, the function is mod sin x by x. So f of x is mod sin x by x, right? So that is equal to, so as x tends to 0 plus, sin x is positive, so mod sin x becomes plus sin x by x. So limit x tends to 0 plus sin x by x, we have a standard formula, this is equal to 1. Next, limit x tends to 0 minus f of x is equal to limit x tends to 0 minus f of x is mod sin x by x. That is equal to limit x tends to 0 minus. So as x tends to 0 minus, that is x is in the negative neighborhood of 0. So x is in the fourth quadrant, the angle x is in the fourth quadrant. So sin x is negative. So mod sin x is nothing but minus sin x by x. So sin x by x tends to 1. So minus sin x by x tends to minus 1. And what is f of 0? The functional value at exactly x is equal to 0. At x is equal to 0, the functional value is equal to 1. So as you can see, the right limit is equal to the functional value, but the left limit is not equal to the functional value. Hence, this implies f of x is discontinuous at x is equal to 0. So if you are asked to check the right continuity and left continuity, so 0 plus is same as the functional value at 0. So I can say that f of x is right continuous, but f of x is not left continuous. F of x is right continuous at x is equal to 0, but f of x is not left continuous at x is equal to 0. So hence effectively it is discontinuous at x is equal to 0. In this question, given that f of x is mod x plus 3 if x is less than minus 3, minus 2x if x is in between minus 3 and plus 3, 6x plus 2 if x is greater than or equal to 3. We are asked to show that fx is discontinuous at x is equal to 3 but continuous at x is equal to minus 3. So a very simple question again, we just need to check the condition for continuity. So what is limit x tends to minus 3 plus f of x? That is in the right neighborhood of minus 3. Where does the function go? That is equal to limit x tends to minus 3 plus. So on the right neighborhood of minus 3. So if you take the real number line, so minus 3 is here. So minus 3 plus means in the interval which is greater than minus 3. So in the interval which is greater than minus 3, that is minus 3 to 3, in this interval, f of x is minus 2x. So this function is minus 2x. So it is a very simple function, you just need to substitute it directly. So minus 2 times minus 3, which is equal to 6. So limit x tends to minus 3 plus f of x is 6. Now limit x tends to minus 3 minus f of x. In the left neighborhood of minus 3, that means you have to consider the function where x is less than minus 3. So if x is less than minus 3, so the function is mod x plus 3. So mod x plus 3. So you can do the direct substitution. It is mod of minus 3 plus 3, which is equal to again 6, because mod of minus 3 is plus 3. 3 plus 3 is equal to 6. So limit x tends to minus 3 plus is 6. Limit x tends to minus 3 minus is also equal to 6. And what is the exact functional value? F of minus 3. At exactly minus 3 also this function works. So mod of minus 3 plus 3, which is also equal to 6. So the right limit is same as left limit is same as the functional value. Hence the function is continuous at x is equal to minus 3. Right? So this is the one of the part. So next, let us see the continuity at x is equal to 3. So limit x tends to 3 plus f of x is equal to. So limit x tends to 3 plus in the right neighborhood of 3, that is greater than 3. The function is 6x plus 2. So 6x plus 2, which is equal to, on direct substitution you get 6 into 3 plus 2 is 20. So now limit x tends to 3 minus f of x in the left neighborhood of 3. That means in the interval which is less than 3. So from minus 3 to 3 this works. So f of x becomes minus 2x. So this is equal to, on direct substitution you get minus 2 times 3, which is equal to 6. So clearly you can see that the right limit is not same as left limit. Hence the function is discontinuous at x is equal to 3. So this function is continuous at x is equal to minus 3 but discontinuous at x is equal to 3. So this is a next type of question. So till the previous questions, you're given the function completely and you're asked to check whether it is continuous at a point or not. So in this question, you're given f of x is equal to 1 minus cos 2x by 2x square if x not equal to 0, k if x is equal to 0. You're asked to find this unknown given that f of x is continuous at x is equal to 0. So in this question, you're given that fx is continuous, you're asked to find an unknown. So if a function is given completely, you'll be asked to check whether it is continuous or not. It is given that it is continuous, so you can find an unknown. So how do you find this unknown k? So using the general condition for continuity. So if the function is continuous at x is equal to 0, limit x tends to 0 plus f of x should be same as limit x tends to 0 minus f of x has to be same as f of 0. So in this question, on the right neighborhood of 0 and left neighborhood of 0, the function is same. The function is same. So you don't need to find two different limits. You can directly find these two by finding a single limit. So limit x tends to 0 f of x. That is, as x tends to 0, means x is not equal to 0, the function is 1 minus cos 2x by 2x square. So I'll find the limit. So the limit is equal to limit x tends to 0. We have solved these types of questions in the topic of limits. So 1 minus cos 2x is 2 sine square x by 2x square. So 2 and 2 gets cancelled. So sine square x by x square. Sine square x by x square as x tends to 0. Sine x by x is 1. Sine x by x whole square is also equal to 1. So this is equal to 1. So limit x tends to 0, 1 minus cos x by 2x square is equal to 1. So the value of this limit is equal to 1. And this has to be equal to the functional value at x is equal to 0. At x is equal to 0, the functional value is nothing but k. So for this function to be continuous, k has to be equal to 1. So that's the answer to this question. So this is a question where you have an unknown. So you can also have two unknowns. If it is given that fx is continuous at two different points, you can find two unknowns from that information. So let us go to a question where you have two unknowns. In this question, you are given that f of x is equal to sine a plus 1 times x plus sine x by x if x is less than 0. So 0 is the point in the left neighborhood of 0. When x is less than 0, this is the function. Exactly at x is equal to 0, the functional value is given as c. And on the right side of 0, the function is this. Root of x plus bx square minus root x by x bx power 3 by 2. Now the question is that it's given that this function is continuous at x is equal to 0. You're asked to find the unknowns a, the unknown b, the unknown c. So you're given one single condition that this function is continuous at x is equal to 0. You're asked to find three unknowns. So let us see if it is possible to find these numbers or not. So it is given that it's continuous at x is equal to 0. Hence the condition is limit x tends to 0 plus f of x is same as limit x tends to 0 minus f of x is same as f of 0. This has to be the condition. So now let us find the right limit. So limit x tends to 0 plus f of x. So limit x tends to 0 plus f of x in the right neighborhood of 0, this is the function. So root of x, this is the first thing that I need to find out. So let this be the 1, so let this be 2, let this be 3. So I'll find each of this and finally equate the numbers. So limit x tends to 0 plus minus root x by b times x power 3 by 2. So this can be very easily solved using the process of rationalization, right? So I'll rationalize the numerator and denominator. Root of x plus bx square plus root x by root of x plus bx square plus root x. So now the numerator becomes limit x tends to 0 plus a square minus b square is x plus bx square minus x divided by b times x power 3 by 2 times root of x plus bx square plus root of x. So x and x gets cancelled. So b and b gets cancelled. So x power 3 by 2 gets cancelled with x square and you will be remained with x power half. It will be left out with x power half. So x power half by this. So if x tends to 0, if x tends to 0. So if x tends to 0, again you're getting 0 by 0 form. So now what you can do is, you can take a root x common from the denominator. So if I take a root x common from the denominator, you get limit x tends to 0 plus. In the numerator you have a root x divided by root x times. So if you take a root x as common, here you have root of 1 plus bx plus root x common, you have a 1 here. So root x and root x gets cancelled. So once the indeterminacy has been cancelled, you can do the direct substitution. So this becomes 0. So 1 plus 1 is 2. So the limit is 1 by 2. That means the right limit is equal to 1 by 2. So now let us go for the left limit. So limit x tends to 0 minus. In the left neighborhood of 0, the function is this. So sine of a plus 1 times x plus sine x whole by x. So I can separate this x because sine x by x is 1. So for this term, I will multiply and divide with a plus 1. So sine a plus 1x by a plus 1x. This tends to 1. This tends to 1. So you get a plus 1 plus 1, which is a plus 2. A plus 1 plus 1 is a plus 2. So the left limit is equal to a plus 2. That means this is a plus 2. And what is f of 0? F of 0 at exactly x is equal to 0, the functional value is c. So if I substitute everything here, so you get half is equal to a plus 2 is equal to c. So this implies a is equal to half minus 2 is minus 3 by 2. C is equal to half. C is equal to half. And as you have seen, the limit, the right limit does not depend on b. So whatever the value of b is, so b can be any real number. So for whatever real number you choose, b really doesn't affect the limit. So this limit will always be equal to 1 by 2 whatever the value of b is. So b can be any real number, so except 0 I say, because b is in the denominator, b cannot be equal to 0. So b can be any real number except 0. A has to be equal to minus 3 by 2. C has to be equal to 1 by 2 for this function to be continuous at x is equal to 0. In this question, given that f of x is a times sine pi by 2 times x plus 1 if x is less than or equal to 0, tan x minus sine x by x cube if x is greater than 0. Given that this function is continuous at x is equal to 0, we are asked to find f of a. So again, we'll use the condition for continuity. So limit x tends to 0 minus f of x has to be same as limit x tends to 0 plus f of x has to be same as f of 0. Has to be same as f of 0. So now let us find each of these limits. So limit x tends to 0 minus in the left neighborhood of 0. 0 minus means less than 0. So this is the function a sine pi by 2 times x plus 1. So that is equal to, so you can do the direct substitution. If x is equal to 0, this becomes pi by 2, sine pi by 2 is 1. So a into 1 is equal to a. So this is the left limit. So left limit is exactly equal to a. So whatever this a is, that is the limit. Next, let us go to the right limit. Limit x tends to 0 plus. So in the right neighborhood of 0, this is the function. So tan x minus sin x by x cube. So this can be done in different ways. This can be done by using tan x is equal to sin x by cos x. That's one way. Or you can use the expansions also. So let us use the direct method, tan x as sin x by cos x. So limit x tends to 0 plus. So if I take sin x by cos x as common, so you get 1 minus cos x divided by x cube. So 1 sin x and 1x gets cancelled, gives you 1, because sin x by x tends to 1. And 1 minus cos x. Limit x tends to 0 plus. So sin x by cos x. Cos x is not problematic, so you don't need to do anything with it. So 1 minus cos x is 2, sine square x by 2. That is 2 sine x by 2 into sine x by 2 divided by x cube is 1x, another x and another x. So sine x by x goes to 1. So you have sine x by 2 here. So I will divide with 2 and multiply it with 4. So sine x by 2 goes to 1. This goes to 1. So this 2 and this 2 gets cancelled. Cos 0 is 1. So effectively the limit is 1 by 2. So right limit is 1 by 2. Left limit is a. What is the functional value? Functional value comes from this function. So if you put exactly x is equal to 0, the functional value is also equal to a. So what is the condition? A is equal to half is equal to a. So effectively, what is the value of a? A has to be equal to half for this function to be continuous at x is equal to 0. So in this video, let us look at different types of discontinuity that occurs in functions. So we have already seen the condition for continuity. So when will a function be continuous? So if limit x tends to a plus f of x is equal to limit x tends to a minus f of x is equal to f of a, then we say that the function f of x is continuous at x is equal to a. So if all these three are equal to a finite value, then we say that f of x is continuous at x is equal to a. Now, so there can be different types of discontinuities. That is, there can be different ways in which this condition does not hold. So the first type of discontinuity is called removable discontinuity. Removable discontinuity. So what is the meaning of this? So if limit x tends to a plus f of x is same as limit x tends to a minus f of x. So if these two limits are same, that is the right limit and left limit is same, that means the limit exists for this function at x is equal to a. But if this is not equal to the functional value at a, we say that you have a removable discontinuity for this function. That is, if the graph is something like this, so if you have a graph which looks like this, so if this is my x is equal to a, so at x is equal to a, the right limit is same as left limit. But if the functional value is something else, so this type of discontinuity is called removable discontinuity, because you can very clearly see if you just change this functional value at a and bring it here, then this function becomes continuous. So without much effort, just by changing the functional value at x is equal to a, you can, to an appropriate value, you can make this function into continuous. This can make this function into a continuous function. So that is why this is called a removable discontinuity. So next you have something called a non-removable discontinuity. So non-removable discontinuity. So non-removable discontinuities can be of three types. So non-removable discontinuity of type 1 is where the right limit is not equal to the left limit. So if limit x tends to a plus f of x is not equal to limit x tends to a minus f of x, if the right limit and left limit are not equal, then we say that the function has a non-removable discontinuity of type 1. That means the graph of the function looks something like this. The right limit at x is equal to a is going somewhere else and the left limit is going somewhere else. So this is called a non-removable discontinuity of type 1. Next, we have a non-removable discontinuity of type 2. So this is where one of these limits or both of these limits do not exist. So if the limits of either the right side or on the left side do not exist, then we say that you have a non-removable discontinuity of type 2. If limit x tends to a plus f of x or limit x tends to a minus f of x do not exist, then we say that you have a non-removable discontinuity of type 2. And next, you have a non-removable discontinuity of infinite type. In this, what happens is, if either of these limits, either this limit or both of these limits goes to plus or minus infinities, that is, if these two limits are not finite limits, that is, if limit x tends to a plus f of x or limit x tends to a minus f of x go to plus or minus infinities, then also we say that the function is discontinuous and it is a non-removable discontinuity of the infinite type. So these are the different ways in which a function can be discontinuous. So in this video, let us look at the algebra of continuous functions. That is, if you have some continuous functions, what happens if you add them, subtract them, multiply them, divide them, composite them, so on. So if you have two functions f and g, both continuous. So if you have two continuous functions, then the sum or difference of the two functions, the product of the two functions, and the ratio of the two functions are all continuous. There is no problem with the continuity of any of these operations. So f and g are both continuous. The sum is also continuous. Their difference is also continuous. Their product is also continuous. Their ratio is also continuous. But with respect to the ratio, you have a small caveat, a small condition. So f by g is continuous at all the points where g is not equal to 0. At all the points where the denominator function is not equal to 0. Because if the denominator function is becoming 0 at some points, at those points this function will not be defined. So for two continuous functions, there is no problem with continuity for any of these operations. Next, if out of f and g, exactly one of them is continuous, exactly one continuous and other discontinuous, if one is continuous and the other is discontinuous, f plus or minus g, this will be discontinuous. The sum of a continuous function and a discontinuous function is always a discontinuous function, or the difference is also a discontinuous function. But with respect to the product and division, nothing can be said. So you have to check actually. Nothing can be said. That means that if you are given specific functions, fg and f by g cannot be said to be either continuous or discontinuous directly, always. So you have to check the functions according to the functions given in the problem. So needs to be checked. And in third case, where f and g are both discontinuous, so f plus or minus g, fg, f by g, nothing can be said about any of these functions. Nothing can be said about any of these functions directly. You have to check the given functions and you have to go for the original condition and check whether the functions are continuous. So if both are continuous, then you have some shortcuts. If one is continuous and the other is discontinuous, you have some shortcuts. If both are discontinuous, you don't have any specific result. You have to check according to the functions given in the problem. So next, we know the behaviors of some very standard functions. We have studied the standard functions in our class 11th, and you know the nature of continuity of those functions because you know the graphs of those functions. So let us just see which of the standard functions are continuous, which of them are discontinuous, and if discontinuous, where are they discontinuous. So first, polynomial functions. Polynomial functions are always continuous. So you can directly use this statement in your problems. If you have a polynomial function, you don't need to prove the continuity of the polynomial function. It's a known fact that polynomial functions are always continuous. You have seen the graphs of polynomial functions also. They never break. Next, rational functions. Rational functions. That is, some polynomial by another polynomial. So rational functions are always continuous. Always continuous except at those points where q of x is equal to 0. Always continuous except where q of x is equal to 0. So as long as q of x is not equal to 0, all the rational functions are always continuous. Next, modulus function. So modulus function is always continuous. Next, so after modulus function, exponential and logarithmic functions. So exponential and logarithmic functions. So these two functions are always continuous wherever they are defined. So modulus function, exponential function, logarithmic function. And the functions nth root of x, y is equal to nth root of x, and y is equal to x power n. So these functions are always continuous. So these are some standard functions which are always continuous wherever they are defined, and you can use them as the standard results. And among the discontinuous functions, standard discontinuous functions which we have, one of the example is signum function is discontinuous at x is equal to 0. Signum function is discontinuous at x is equal to 0. Integer part of x and fractional part of x, these are discontinuous at integer values of x, at all x which belong to integers. So signum x is a discontinuous function. Integer part of x and fractional part of x are discontinuous at x belongs to z. Next, trigonometric functions are always continuous in their domain. It is sin x, cos x are continuous on real numbers. Tan x and cosecant x. Tan x and secant x are continuous at all real numbers except odd multiples of pi by 2, because that's the domain of tan x and secant x. Similarly, cot x and cosecant x are continuous at all real numbers except multiples of pi. So sin x, cos x, tan x, secant x, cosecant x, and cot x. So all the trigonometric functions are continuous in their domain. All trigonometric functions are continuous in their domain. Similarly, all inverse trigonometric functions are also continuous in their domain. So inverse trigonometric functions are all continuous within their domain. Continuous in their respective domains. So these are the natures of continuities of different types of functions, and you can use this information directly in your questions. Whenever you want to reason some questions out, if you have a modulus function, you can reason it that modulus function is always continuous, and from that reasoning you can go forward. You don't need to prove that mod function is continuous because it is a well-known fact. Because from the graph you can very clearly see that modulus function is a continuous function everywhere. Next, if you look at the continuity of composite functions. Composite functions. So we have two functions f of x and g of x. We have two functions f of x and g of x. And we are talking about the composite function g(O)f of x. So we know that g(O)f of x is nothing but g of f of x. Now, if f of x is continuous at x is equal to a, if fx is continuous at x is equal to a, and gx is continuous at f of a. If x is continuous at x, fx is continuous at x is equal to a, and gx is continuous at f of a, then g of f of x is continuous at x is equal to a. So this is how the continuity of composite functions work. Is if you have two functions, if you take the machine interpretation of functions. So g of f of x, that means x is going first into f of x, and whatever is the output is going into g of x. Now if this composite function or if this composite machine has to be continuous at x is equal to a, then at x is equal to a, f of x has to be continuous, and the number that is coming out of this is f of a, and g of x has to be continuous around f of a. So if that is so, then g(O)f of x will be continuous at x is equal to a. So if this doesn't hold good, so you need to check separately for the continuity of the function using the standard definition. So if this happens, then we are sure that it is continuous. If this does not happen, then we are not sure whether it is continuous or discontinuous. We have to check according to the given question. So we have seen how this continuity works for sum, difference, multiplication, division, composition of different functions. For example, if you take sine of mod x, f of x is equal to sine of mod x. Now this is a composite function. This is a composition of mod x and sine x, right? So as we know, mod x is always continuous, sine x is also always continuous. So sine mod x will always be continuous. So if f of x and g of x are continuous on x belongs to R, that is, if these two functions are always continuous, then their composition will always be continuous. So this is a very important thing to understand. The composition of two continuous functions. The composition of two continuous functions is also continuous. That is, if two functions are always continuous, then the composition is also always continuous. And if you want to check the continuity at a particular point, so this is how you check. So if f of x is continuous at x is equal to a and gx is continuous at f of a, then g over f is continuous. If this does not happen in a particular question, so you have to go to the particular functions given in the question and find the limits and check the continuity of the function. In this question, you are asked to discuss the continuity of f of x is equal to mod x plus mod x minus 1 in the interval minus 1 to 2. So if you look at the function f of x, it is the sum of two functions. So f of x is equal to mod x plus modulus of x minus 1. So let us consider mod x as the function g of x and mod x minus 1 as the function h of x. And we have already seen that mod x is always continuous. Mod x is always continuous. That is, g of x is always continuous. Next, what can you tell about mod of x minus 1? So mod of x minus 1 is a composite function made of mod x and x minus 1. So if you take two functions, px is equal to x minus 1, qx is equal to mod x. So mod x minus 1 is nothing but q of p of x. So what is q of p of x? It's nothing but q of x minus 1, which is equal to mod of x minus 1. So mod x minus 1, which is h of x, is a composite function of mod x and mod x minus 1. And x minus 1 is a polynomial function. Q of x is a modulus function. So we know that mod x is always continuous. A polynomial function of degree 1 is always continuous. So the composition of q and p is always continuous. That means mod x minus 1 h of x is also always continuous. So mod x is always continuous. Mod x minus 1 is also always continuous. Hence, the sum of two continuous functions is always continuous. So mod x plus mod x minus 1 is always continuous. That is, at all real numbers, it is always continuous. Hence, f of x is continuous in the interval minus 1 to 2 also. So in this question, given that fx is x cube minus x square plus 2x minus 2 if x is not equal to 1, 4 if x is equal to 1. And you are asked to locate the point of discontinuity. So as you can see, this function is defined on all real numbers. It is a piecewise defined function. When x is not equal to 1, you have a definition. Exactly when x is equal to 1, you have another definition. Now you are asked to locate the point of discontinuity. So you cannot search over all real numbers. So we'll use standard logic. So if you see the nature of this function. So what is the nature of f of x? As long as x is not equal to 1. As long as x is not equal to 1, it is a cubic polynomial. This is a cubic polynomial. And we have a result which says that polynomial functions are always continuous wherever they are defined. So the polynomial functions are always continuous wherever they are defined. That is, as long as x is not equal to 1, the function is continuous. So if by chance there is a problem of continuity, it has to occur at x is equal to 1. So I am not saying that it is not continuous at x is equal to 1. We need to check whether this function is continuous at x is equal to 1. If at all there can be some problem, it has to be at x is equal to 1. As long as x is not equal to 1, it is a polynomial function, hence continuous. So check continuity at x is equal to 1. Check the continuity at x is equal to 1. So limit x tends to 1 f of x. So I'm not doing 1 plus and 1 minus separately because you have the same function on both sides. So limit x tends to 1 f of x is limit x tends to 1 x cube minus x square plus 2x minus 2. So if you put x is equal to 1, 1 minus 1 plus 2 minus 2 is equal to 0. Hence the value of limit is equal to 0. But what is f of 1? F of 1 is given as 4. So these two are not equal to each other. The limit value is not equal to the functional value. Hence fx is discontinuous at x is equal to 1 is the answer to this question. In this question, you are asked to show that fx is equal to mod of sin x plus cos x is continuous at x is equal to pi. So you can directly check the condition for continuity for the function. So limit x tends to pi f of x. Let us find limit x tends to pi f of x. That is limit x tends to pi mod of sin x plus cos x. So this is not an indeterminate form on direct substitution. So we can do the direct substitution, there is no problem. So sin x, sin pi is 0, cos pi is minus 1. So 0 plus minus 1 is minus 1 and mod of minus 1 is plus 1. And what is f of pi? That is if you directly substitute pi in the place of x, mod of sin pi plus cos pi, which is 0 plus minus 1, which is minus 1, mod minus 1 is again equal to 1. So limit value is 1, the functional value is also equal to 1, hence continuous at x is equal to pi. So let us take this question. So in this question you are given that f of x is limit n tends to infinity sin x power 2n. So where n belongs to integers. You are asked to find the points of discontinuity of this function. First, here f of x is defined in terms of limit and the variable of limit is n and n is in the power. So let us try to analyze this limit. So limit n tends to infinity sin x power 2n is nothing but sin square x whole power n. As n tends to infinity, you have to raise sin square x to the power n. So any number power n, as n tends to infinity, the value depends on what the value of the base is. So this is equal to 0 if sin square x is less than 1. If sin square x is less than 1, if this is a fraction, then as you raise a fraction to a power which is very large, then the number goes to 0. For example, if you take a number 1 by 2 and raise it to power infinity, this becomes 1 by 2 power n, which goes to 0. So if this number is less than 1, then this limit goes to 0. But sin square x is always non-negative because you have a square, so the other limit will be 0 to 1. And this will be 1 if sin square x is exactly equal to 1. If sin square x is exactly equal to 1, exactly 1 power any number is equal to 1. And this is equal to infinity if sin square x value is greater than 1. So these are the conditions. So that means f of x is equal to 0 if, so what is the meaning of sin square x is in between 0 to 1? That means sin x is in between minus 1 and plus 1. So there is no equality, sorry, because you don't have equality at 1. So as long as sin x is in between -1 to +1, sin square x is in between 0 to 1. Right? So f of x will become 0. And sin square x is equal to 1 means sin x is equal to plus minus 1. So fx is equal to 1, sin x is equal to plus or minus 1. And infinity, if sin square x is greater than 1, this never happens because sin x is always in between -1 to +1. So this case does not arise. So this is my function. And if you think in terms of the values of x, when will sin x be in between -1 and +1? So sin x, when will sin x be equal to +1 or -1? So sin x will be +1 or -1 at odd multiples of pi. So this implies x is equal to 2n plus 1 times pi by 2. So when x is an odd multiple of pi by 2, then sin x will be plus or minus 1, and at those points fx is equal to 1. And at all the remaining values, at all the remaining other values, the value of f of x is equal to 0. Now you are asked to find the points of discontinuity of this function. So as you know, f of x is equal to 0, f of x is equal to 1. They are continuous wherever they are defined because these are constant functions. But if there are some points of discontinuity, they may happen at the boundary points because it is a piecewise defined function. So at all r minus of 2n plus 1 times pi by 2, if the function is continuous. So if at all there are some problems of continuity, they occur at the boundary points. So at the boundary points, as you can see, the functional value is 1, but the limit value is equal to 0. So if you take any point of the form 2n plus 1 times pi by 2, exactly at this point the functional value is equal to 1. But around this point, when x is not equal to 2n plus 1 times pi by 2, the functional value is going to 0. Hence the graph will be something like this. You have a hollow dot here, you have a hollow dot here, and you have 1 here. So hence, as you can very clearly see, fx is discontinuous at all points of the form 2n plus 1 times pi by 2 because the limit value is different from the functional value. So what are the points of discontinuity? X is equal to 2n plus 1 times pi by 2 where n belongs to integers. So that is the answer to this question. So in this question, given that f of x is 1 by x square minus 17x plus 66, and then f of x by x plus 2 is discontinuous at x is equal to what? This is the question. So this is an example of a composite function. So let u is equal to x by x minus 2. That is, u is a function of x. So let us say that u is x by x minus 2. So this implies the given function is nothing but f of u. F of u is nothing but, according to this function, 1 by u square minus 17u plus 66. So this is a quadratic. You can very clearly see that this can be very easily factorized as u minus 11 times u minus 6. So as you can see, f of u is a rational function. So rational function is always continuous except the points where the denominator is equal to 0. It is when u is equal to 11 or 6, this f of u has problems of continuity. So when u is equal to 11 or 6, the function is discontinuous. And also, you have to be very clear here. And also, f of u is not defined at x is equal to 2 because u is not defined at x is equal to 2. So only after f of u is defined, you can think about the continuity or discontinuity. But u of x is not defined at x is equal to 2. So if u is not defined, obviously f of u is also not defined. So when u is equal to 2 also, the function is discontinuous. because the function is not defined. So that means x by x minus 2 is equal to either 11 or 6. Sorry, here u is not equal to 2, x is equal to 2. When x is equal to 2, u is not defined. Hence x is equal to 2, the function is discontinuous. And after u is defined, f of u is not defined when u is equal to 11 or 6. That is x by x minus 2 is equal to 11 or 6. So this implies x is equal to 11x minus 22. So 22 is equal to 10x. X is equal to 22 by 10 or 11 by 5. So one point is x is equal to 11 by 5. Or x by x minus 2 is equal to 6. This implies x is equal to 6x minus 12. 5x is equal to 12. X is equal to 12 by 5. So this is the next point. So f of u, f of x by x minus 2 is discontinuous at 3 points: 2, 12 by 5 and 11 by 5. In this question, you're given that f of x is equal to 1 by 1 minus x. And you're asked to find the points of discontinuity of f(3n) of x, where fn of x is fo, 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 so on, of. That is, f1 is f of x, f2 is f of x, f3 is f of x, so on. And you're asked to find the points of discontinuity of f composited 3n times. That is either 3 times or 6 times or 9 times, so on. So let us try to analyze what happens when you composite this function again and again with itself. So fx is 1 by 1 minus x. Clearly f of x has problems when x is equal to 1. When x is equal to 1, fx is not defined. So if you go to f of x, that is f2 of x, that is equal to 1 by 1 minus of 1 by 1 minus x, right? That is equal to 1 by 1 minus x minus 1 is minus x by 1 minus x. That is equal to x minus 1 by x. So f of x has problems at x is equal to 0. Now let us composite again. f3 of x is equal to f of x, that is equal to, so f of f2 of x, that is equal to f2 of x is this, so 1 by 1 minus of x minus 1 by x, that is equal to, if you take the LCM, x minus x plus 1, denominator is 1, this goes up, which is equal to x. So that means after compositing function 3 times, you're getting f3 of x is again equal to x. So f4x is nothing but f of f3x, which is equal to again f of x. So after 3 times, the next time f4 of x is again equal to f of x, f5x is f2x, f6x is again f3x. That means this function is, the composite function is going on repeating itself. And after every 3 stages, it again goes back to x. So if you look at just this function, f3n of x is equal to x, there are no problems of discontinuity for this function. But on the way of coming to f3 of x, we had problems at x is equal to 1 and x is equal to 0. That means at x is equal to 1, the function f3x is not defined. And at x is equal to 0 also, f3x is not defined. Hence, these are the points of discontinuity. So the points of discontinuity are x is equal to 0 and 1. So next, Let us look at this question. F of x is equal to 1 if x belongs to rational numbers, minus 1 if x does not belong to rational numbers. That is, if x belongs to irrational numbers. So this is the function, and you are asked to discuss the continuity of this function f of x. So let us say that we'll try to discuss the continuity at a point A. So let A belongs to some real number. That is, A is a real number. So if A is a real number, it will either be A. It either belongs to Q or belongs to Q complement, that is irrational. So if you take any real number, it will either be a rational number or an irrational number. So let us say whatever this real number is, if you try to find limit x tends to a f of x. So limit x tends to a f of x. So a can be either rational or irrational number. So this a will be some number on the real number line. So what is the meaning of limit? So as x tends to a, that is x goes closer and closer to a, that is x lies in the neighborhood of a. Where does f of x go? So as we know, in the neighborhood of any number. So you take a neighborhood of any interval. We know that every interval of real numbers contain infinite number of rational numbers and infinite number of irrational numbers. So within any small interval of real numbers, you can insert infinite number of rational numbers and infinite number of irrational numbers. So if x is going closer and closer to a, that is, if x belongs to the infinitesimal neighborhood around a, so within this neighborhood there are infinite rationals and infinite irrationals. That is, the value of f of x oscillates between 1 and minus 1 infinite times. F of x doesn't tend to any particular value. So limit x tends to a f of x does not exist. That is, for this function, the functional values exist for all numbers. Take any number, the functional value exists. It will be either plus 1 or minus 1. But at any point, limit x tends to a f of x does not exist. So this is an example of non-removable discontinuity of type 2. That is, limits don't exist. Limit x tends to a plus does not exist. Limit x tends to a minus also does not exist. So if you are asked to discuss the continuity of f of x, the answer will be that this function is discontinuous at every x belongs to real numbers.